Hello and welcome. So the first topic, at least I like to think of this as the first topic in Calculus AB is limits. So under limits, there's kind of four subcategories. You have limits on a graph. So let's say limits on a graph. You have to understand that. You also have to understand like directional limits or one-sided limits. I like to think of them as one-sided limits because you're looking at them from one side. So that's when you have like a limit as x approaches 2 from the left, right? Or from the right, alternatively. And then the third subdivision is limits at infinity. So you have to understand how to evaluate limits at infinity. And the last one is L'Hopital's rule. So if you understand these four things about limits, you understand the first topic in Calculus AB. So the first thing about limits that you have to understand is limits, evaluating limits based on a graph. So if we're given this graph and we have, for a first example, limit as x approaches 2 from the right. So if there's a plus, next to the 2, then we're approaching from the right. We're approaching from the positive side, right? The right plus positive. Anyways, so to do this, we just start somewhere to the right of 2 on the graph, and we just approach 2. And as we get closer and closer to 2, the y value we approach is 3. So we don't have to worry about the fact that there's a separation here. We don't have to worry about any of that. We're not even worried about the point at 2. We're just worried about where the graph goes as x gets closer to 2 from the right side. So then similar but a different example, 2 from the left, or where there's a minus, so from the negative side, we're just approaching 2 from the left. It doesn't matter that there's an open circle. It doesn't matter that it's not continuous here. All that matters is as x approaches 2 from the left, we get closer and closer to -3. So -3 is what we approach. And then a third example, limit as x approaches 2. Now we're approaching from both sides. So as we approach from the left, we get -3. As we approach from the right, we get +3. But obviously, -3 and +3 are not equal. So if the limits from the left and the right don't agree, or they're not equal, then the limit from both sides does not exist. Alternatively, if this graph looked like this, and now we're approaching 2 from both sides, it's continuous, so the limit would exist, and it would be, let's say this is at y equals 1, the limit would equal 1. So that's really all the basic, the only basic things you need to know for evaluating limits based on a graph. So the next thing we have to look at is one-sided limits and not 0 over 0 limits. So if you have a limit and it asks you, I'm not really going to go through any like example problems. I'm just going to kind of explain what if you see this, then you should do this. So if you have a limit that, let's say, approaches 3 from the left, what you're going to do is choose a number that's just to the left of 3. For example, 2.9 or 2.999, something like that, and then plug that into the limit, and whatever the outcome of that is your answer. So for example, well, I guess I will show an example. If you had a limit of as x approaches 3 of some function, and the output was, for example, 4 over -0.0001, this would be negative infinity. It would be equal to negative infinity, because this is the same as -1 over 1,000 or 10,000. So 4 over all of this is the same as 4 times negative 10,000, which is essentially negative infinity, because as it gets closer and closer to 3 from the left, like 2.9999999, this number is going to get smaller and smaller, and this is going to approach infinity. And it's the same thing if it was from the right. You just choose 3.1 or 3.00001 or 3.0001. You get the idea. And then whatever the outcome is when you plug it into the function is your answer. So that's one-sided limits. And then non-zero over zero limits are normal limits or number over zero limits. So if you have just a normal limit where you just plug in the number and you get a number that exists, then that's your outcome. So that's easy enough. And if you have a limit where you plug in the number and you get a number over zero, what you're going to want to do is go back to these one-sided limits. Let's say it approaches 3. Now you plugged in 3 and got a number over 0. So what you're going to want to do is go back and plug in 3 from the left, so 2.99999, and then also go back and plug in 3 from the right, so 3.0001. And if they agree, let's say from the left it approaches infinity, and then from the right it approaches infinity, then that would be your answer. Let's say, for a different example, if from the left it approaches negative infinity and from the right it approaches positive infinity, then your answer would be does not exist. So your 3 possible answers are negative infinity, positive infinity, or does not exist. So the next thing you have to understand is limits at infinity. And this is pretty easy. It can kind of be like conceptually a little weird to understand, but it's not very hard to actually do in practice. So if you have a limit that approaches positive infinity, for example, and the function is, let's say, 4x cubed minus 3x squared plus 4 over 5x to the power of 4 minus 3x squared. You can ignore all the items on the top and the bottom that are raised to a power that's less than the highest power. So on the top, it's the highest power is 3, so we can ignore that and ignore that. And the bottom, the highest power is 4, so we can ignore 3x squared. So now we have 4x cubed, not minus anything, so I'll erase that. We have 4x cubed over 5x to the power of 4. Now we can, since the powers are different, we can ignore these because we can ignore the constants. Because if we had infinity times 4, that's obviously a very large value, but infinity squared, for example, is much larger. So infinity raised to a power is always greater than infinity times a constant. So if they're being raised to different powers, it's the difference because of the constants is negligible. Because this one is raised to another power of infinity, so it's multiplied by infinity again, it's going to be like a so much greater value that multiplying it by 5 or by 4 is not really going to make a difference that means anything. So now we have x cubed over x to the power of 4. So just with some algebra, we can cancel out those x's and we can have 1 over x. So now with 1 over x, we plug in infinity because this was limit approaching infinity. And 1 divided by infinity, so 1 divided by infinity is essentially 0, because 1 divided by 5 is 0.2, right, which is a small number. But then if we divide it by 10, we have 0.1. And if we keep making that denominator larger and larger, it'll eventually just be essentially 0. So this is going to equal 0. And that's kind of just the procedure for any function. If you have limit approaching infinity or negative infinity, you just find what the highest power is, and then you just do algebra like that. You can ignore everything else. And then the only kind of edge case is if these are the same power. In that case, you would do the same thing. So we could go through, I'll draw it up in this corner, go through the same thing. Let's say we get to this point, we have 4x to the power of 3 over 5x to the power of 3. We cancel the x's, right? Because they're the same power. And then we have no more variables to plug in infinity. So our answer is just 4 over 5. So it's really the same procedure for everything. So the last thing you have to understand that has to do with limits for calculus, at least calculus AV, is L'Hopital's rule. So this is pretty easy to do, but you have to understand how to take derivatives. So I guess it kind of reaches forward into future topics, but I'm going to assume that you know how to take derivatives for this to work. So if you plug a number into a limit and you get 0 over 0 or something like infinity, well, it's not a great infinity, over infinity, then you have to, or you can use L'Hopital's rule. So the way you do this is, let's say we have a function, limit approaches some number that would make this function 0 over 0. And let's say our function is 4x cubed minus 3, or plus 3x squared plus 4 over 7x squared minus 2x, I guess, minus 1. So let's say we plugged in a number to this limit and we got 0 over 0. So now what we need to do is take the derivative of the top and the bottom separately. So we're not using the quotient rule or anything like that. We're taking the derivative of the top and then the derivative of the bottom. So 12x squared plus 6x over 14x minus 2. So now what we would do, now that we've taken the derivative of the top and the bottom separately, we would go back and take this number and plug it back in, and then hopefully we would get a valid outcome, like a valid value for our limit. And let's say we don't. Let's say we plug in the number and we still get 0 over 0. Then we can just keep repeating the process. So we take the derivative again, just 24x to the power of 1 plus 6 over 14. And now we plug in the number again, and hopefully we get a valid output. But as so long as you keep getting 0 over 0, you can keep doing L'Hopital's rule. Thanks for watching. I hope this video was helpful. And if you have any questions or comments or requests for future videos, please comment. Thank you.